Hello, my name is Daisuke Oak. It is my great pleasure to introduce our research under the title How to Reduce the Bit Width of an Ising Model by Adding Auxiliary Spins. We have proposed a completely new method to overcome the hardware limitation of annealing machines dedicated to combinatorial optimization programs. There are three major contributions to our research. First, we propose embedding methods for reducing the bit width of interaction and external magnetic field coefficients in the Ising model by adding auxiliary spins. The Ising model will be explained later in the introduction part. Next, the mathematical proof shows that the ground states of the Ising model obtained by our proposed methods are the same as the ground states of the original one. This is the world's first proposal to reduce the bit width of interaction and external magnetic field coefficients theoretically. Finally, experimental evaluations using a real annealing machine for typical combinatorial optimization programs confirm that our proposed methods successfully obtain the ground states equal to the original ones. This is the outline of this presentation. First, I will explain the terms necessary to introduce this research. Next, I will present the motivational background. Then, I will explain the naive method and our proposed methods. We compare these methods and show that our research successfully reduced the bit width of coefficients. Finally, I will conclude my presentation with a summary and future work. This slide gives a brief explanation of combinatorial optimization programs. Combinatorial optimization programs are to find a combination of decision variables optimized under various constraints. Well-known programs are a graph partitioning program, a max-cut program, and a traveling salesman program. Since these programs can be difficult to solve on a von Neumann computer, there are many trials to solve them on a non-von Neumann computer called an annealing machine. This slide shows the annealing machine currently being developed. Machines with various implementation methods have been developed. When using an annealing machine to solve combinatorial optimization programs, we use a model called the Ising model. An Ising model is a statistical mechanics model defined on an undirected graph. The Ising model consists of spins, interactions, and external magnetic fields. A spin sigma I is defined on at the vertex I. A spin has a value of either +1 or -1. The slide shows an example of the Ising model. The figure on the left is an Ising model with an initial state, and the figure on the right is an Ising model with a ground state. The ground state represents the state where the Ising model has the lowest energy. The energy can be defined as this equation. An annealing machine searches for the ground state of the Ising model. In other words, if the optimal solution of the combinatorial optimization programs can be mapped to the ground state of the Ising model, the solution of the combinatorial optimization program can be solved by the annealing machine. This slide integrates the contents described in the previous slides and shows the process of obtaining a solution to a combinatorial optimization program using an annealing machine. There are 5 phases to obtain a solution. In phase 1, a combinatorial optimization program is formulated into a logical Ising model consists of the objective function and the penalty function. In phase 2, the Ising model formulated in phase 1 is embedded onto a physical Ising model or a real annealing machine. In phase 3, an annealing machine searches for the ground state of the Ising model. In phase 4, the state of the logical Ising model is restored from the state of the physical Ising model after annealing. In phase 5, the state of the logical Ising model is interrupted as the solution to the program. I will explain the motivation for this research. We focus on the bit width of the coefficients of the Ising model. There are 2 reasons. First, the bit widths of coefficients are limited in digital annealing machines, which depend on the annealing machine implementation, as explained before. Second, the actual annealing machine using quantum effect are susceptible to errors due to the coherence control errors, diabatic transitions, and thermal noises. To overcome these problems, we propose the bit width reduction method to convert the original Ising model to a transformed one equivalently. Before explaining our proposed method, I will explain a naive method. The easiest way to reduce the bit width is to shift all the coefficient bits to the right by several amounts. The slide shows 3 Ising models. The Ising model on the left is the original Ising model. In the middle, all the coefficients are shifted to the right by 1 bit. In the right, all the coefficients are shifted to the right by 2 bits. The bit shifts are very easy to implement. However, the ground state after applying the bit shift can be changed and the combinatorial optimization programs can be well solved. This slide and the next slides explain our proposed method. In our proposed method, by adding extra spins, the bit width of the coefficient can be reduced without changing the ground states. First, I'll explain how to reduce the bit width of the interaction coefficients. I'll show you how to extend the interactions by adding extra spins. It is shown in the upper left. By adding the spin sigma x between sigma I and sigma j and setting the interactions as shown in the figure, the interactions of the original Ising model can be extended without changing the ground states of the Ising model. Next, I'll introduce a method to reduce the bit width of the interaction coefficient by using the interaction extension method. First, we divide the interaction into 2. At this time, please note that the original interaction coefficient is kept by summing up these divided interaction coefficients. Next, we add an extra spin to the interaction of one of the 2 parts and extend the interaction. By doing this, we can reduce the interaction bit width. An example is shown in the figure below. In the example, the 4-bit interaction coefficient is reduced to 3 bits once. Next is a method to reduce the bit width of the external magnetic field coefficient. The figure on the left shows how to reduce the bit width of the external magnetic field coefficient. By connecting the sigma I and the added extra spin sigma x, as shown in the figure, the bit width of the external magnetic field coefficient can be reduced without changing the ground state. An example is shown in the figure on the right. In the example, the 4-bit extra magnetic field coefficient is reduced to 3 bits. Next is a method to reduce the bit width of the external magnetic field coefficient. The figure on the left shows how to reduce the bit width of the external magnetic field coefficient. By connecting the sigma I and the added extra spin sigma x, as shown in the figure, the bit width of the external magnetic field coefficient can be reduced without changing the ground state. An example is shown in the figure on the right. In the example, the 4-bit extra magnetic field coefficient is reduced to 3 bits. Our paper mathematically proves 4 important theorems. 2 of the 4 are shown on this slide. Theorem 2 is a theorem for reducing the bit width of the interaction coefficient. Theorem 4 is a theorem for reducing the bit width of the external magnetic field coefficient. Please refer to the paper if necessary. This slide compares the naive method with the proposed method. The proposed method reduces the bit width without changing the ground states. It is proved that the ground state of the Ising model is not changed by our methods. This slide shows an example of reducing the bit width. The figure on the left shows the original Ising model and its ground state. The middle figure shows the Ising model and its ground state where the bit width is reducing by 1 bit using the naive method. You can see that the ground states are increased and some of them do not match the original ground state. The figure on the right shows the Ising model and its ground state, where the bit width is reduced by 1 bit from using the proposed methods. The ground state is the same as the one on the left. It is great. It is a summary of my presentation. In our research, we proposed a new embedding method for annealing machines. They transform unlimited bit width coefficients into limited bit width coefficients. They reduce the coefficient bit width by adding auxiliary spins. It is mathematically proved that the ground states of the Ising model obtained by the proposed methods are not changed from the original ones. As a future work, we challenged an embedding method that combines the topology transformation and the proposed method for annealing machines. Thank you very much for listening. That's all.